To the second standard, we are to compare two fractions with different numerators and different denominators, for example, by creating common denominators or numerators, or by comparing to a benchmark fraction such as 1/2. Recognize that comparisons are valid only when the two fractions refer to the same whole. Record the results of comparisons with symbols greater than, equal, or less than, and justify the conclusions, for example, by using a visual fraction model. Okay, so first let's look at cases like, let's compare these two fractions. Let's say we have 4/9 and let's say 7, let's say 9/17. Which one is greater? Well, here's the way I look at it. Right, this is really 4 copies of 1/9. So this is 4 copies of 1/9. And this is 9 copies of 1/17. If I double each one, right, I will have 8 copies and 18 copies. Now, 18 copies of 1/17 is greater than 1, but 8 copies of 1/9 is less than 1. Hence, it's easy for me to conclude that this is greater than that. Right? You may immediately recognize that 1 is greater than 1/2 and 1 is less than 1/2. So, if this were a number line, 4/9 would be somewhere here, very crude approximation, and this would probably be 9/17. So, something along those lines. Now let's look at a case like this. Let's look at 7/10, or let's look at 9/13. Which one is greater? It's difficult to tell just upon inspection. Now, let's consider the case in which the denominator is the same. What's greater, 3/5 or 4/5? It's easy for us to conclude that it's greater. What's greater, 21/25 or 24/25? Clearly, we have 21 copies of 1/25, and here we have 24 copies of 1/25. There's the same size, therefore, we have 3 more copies over here, therefore it's clearly greater. So, is there a way for us, as long as the denominators are on equal footing, for us to obtain? Let us go back to this original theory of equivalent fractions. A over b equals n times a over n times b. Now, let's go back to our comparison. 7/10 and 9/13. Which one is greater? Well, I established that according to the theory of equivalent fractions, I can multiply this by this if I want to. I could multiply it by 3 if I want to, so on and so forth. Provided they're the same number, I could do that. Now, we're going to use a very useful information. Essentially, we're going to use the fact that multiplication is commutative to put them on equal footing. All we have to do is multiply the other denominator, each denominator, by the other one. So, for example, over here, I'm going to multiply each side by 13. And over here, I'm going to multiply each side by 10. See, this is all based on the fact that 10 times 13 is equivalent to 13 times 10. Multiplication is commutative. Therefore, now I have 91 over 130 and 90 over 130. So, as we can see, this one is greater, but not by much. Therefore, 7 over 10 is the greater one. So, in general, right, let's just have these represent arbitrary whole numbers. If we are trying a surefire way to get the denominators on equal footing is to multiply each of these by d, and each of these are going to be multiplied by b. Now, because these are the same, essentially all we have to do is compare this to this. So let's go back to our original statement. In order to see which one is greater, essentially all we have to say is which is greater, A times D or C times B. If this is greater, this will be greater. If this is greater, this will be greater. But what's very important to understand is that it's an extension of getting the denominators. Let's look at more examples. Let's look at 4/5 and 7/9. Right? According to our recent, what I just discussed, this one is 4 times 9 gives us a value of 36. This one gives us a value of 35. Therefore, clearly 4 over 5 is greater. Now, that is essentially a shortcut for getting the fractions on equal footing. Right? Because now we have 36 over 35 or 35 over 45. It should be 45. Right? This is clearly greater. So that is an easy way to see which fraction is greater, but one should understand that it's a consequence of getting the fractions on equal footing.